averaging and average aggregation. Both methods share a similar overall framework. Everyone, I will now introduce the server-side aggregation part. My name is Honglei Zhang, and I'm from Beijing Jiangdong University. First, I would like to express my sincere regret for not being able to attend the conference in person due to personal reasons. Therefore, I will be delivering this presentation online. If you have any questions during this talk, please feel free to email me. In this section, we will focus on the personalized global aggregation process in Federated. In Federated, there are two main mechanisms to achieve personalization. One is the client-side adaptation mechanism, as introduced earlier by Zhiwei, and the other is the server-side personalized global aggregation mechanism, which we will discuss here. The core idea of the server-side aggregation is to aggregate local models uploaded from multiple clients into one or several personalized global models. Moreover, the key function of this mechanism is to embody data locality while achieving knowledge globally across multiple clients through aggregation modules like famous federated averaging algorithm. This is the outline for this section. We will focus on the formal definition of global aggregation, the main challenges it faces, and its primary topology. And then we will introduce several representative methods for global aggregation in detail. And finally, summarize and discuss future directions. Regarding the formal definition of global aggregation, we mainly highlight two classic aggregation methods, the federated averaging and average aggregation. Both methods share a similar overall framework, which involves performing a weighted summation of model parameters updated from multiple clients, where U plus denotes the site of clients participating in the upload. The key difference between the two methods lies in the aggregation coefficients, also known as aggregation weights. The federated average assigns weights based on the relative size of each client's local data, while average aggregation assigns equal weights to all participating clients. These parameter settings also gave rise to several challenges during the global aggregation process. For example, due to the use of simple averaging coefficients, data heterogeneity, and model heterogeneity under the federated settings cannot be effectively addressed. Besides, averaging models from all clients can result in severe aggregation inefficiency, making it necessary to select representative clients for more efficient parameter aggregation. And furthermore, during the aggregation process, it's crucial to effectively balance the contributions of the global model and the local models. This is particularly important because recommendation tasks inherently involve significant data heterogeneity and require strong personalization. Therefore, it's necessary to carefully consider the weighting of local personalized models during the aggregation. To address the challenges mentioned above, researchers have proposed a variety of effective aggregation mechanisms. We categorize these measures into the following main tabs, like clustering-based aggregation, attention-based aggregation, graph-based aggregation, and composite aggregation. So next, we will introduce the core ideas behind each of these approaches one by one. And the first category is clustering-based aggregation. Let's begin by recall the definition and main mechanisms of clustering measures. And the clustering is a form of unsupervised learning paradigm that groups data points based on similarity functions, such as Euclidean distance or cosine similarity. The primary goal of clustering is to partition the entire dataset into multiple groups where similar data points are grouped together, and these similar data points are separated into different clusters. There are so many clustering algorithms, like the famous k-means algorithm. In p-Federated setting, where a large number of participating clients often have highly non-ID distributions, clustering-based methods can be employed to mitigate this issue. Among clustering-based aggregation approaches, two earlier representative works are FitFast and Perfect. Both methods use clustering methods to group clients with similar data distributions and then perform group-wise parameter aggregation to allocate the problem of data heterogeneity in federated settings. The main difference between them is FeedFast selects a representative clients from each cluster for aggregation after clustering, while Perfect performs aggregation within each group after clustering. Recently, researchers have discovered that the clustering-based methods mentioned above may suffer from privacy linkage and the cause of dimensionality. Additionally, experiments have shown that the classic k-means algorithm can lead to clustering failure in the p-Federated scenario, where most clients are assigned to the same cluster, resulting in imbalanced clusters. So to address this issue, Federated proposed a co-clustering mechanism to allocate the course of dimensionality. Specifically, the method first clusters clients based on based on item categories, and then perform co-clustering based on item categories to better group clients. This two-step process helps mitigate the dimensionality issues associated with the classic k-means approach. The second category is attention-based global aggregation. So let's first review the concept of the attention mechanism. Originally from the field of computer vision, attention is a technique in deep learning that enables a model to focus on the most relevant parts of the input when performing a task, like image classification in computer vision and binary classification in recommendation tasks. So the main idea is that instead of processing all input information equally, attention assigns different weights to different parts, allowing the model to focus on the most important features. This concept is particularly useful for addressing many of the issues that arise from federated averaging in global aggregation. So, one representative method in this category is FeedATT. It specifically proposes an attention mechanism for the server-side model aggregation process, which takes into account the contribution of different clients relative to the global model. This allows for differential aggregation of parameters from various clients. Experimental results have demonstrated its superiority over federated average. Building on this, researchers have further proposed a layer-wise attention aggregation method named PFeed-LA. This method considers fine-grained aggregation coefficients at the layer level, enabling a personalized global aggregation. The aggregation coefficients are learned through a well-defined hypernetwork, allowing for more precise contribution allocation. Experimental results have demonstrated that layer-wise aggregation outperforms model-wise aggregation in terms of performance. The third category is graph-based global aggregation. As we all know, graph learning, as many of you may be familiar with, is a technique that learns from graph-structured data, where data points are connected by edges that represent relationships. The mainstream graph learning models include earlier methods like graph matrix factorization, as well as more recent and popular approaches such as graph neural networks and large language models. The p-filter graph method treats each client as a node in the graph and then constructs a graph structure to learn the weight of each node. On the right, we show the loss function of the proposed method, where the first term represents the task-specific loss, such as cross-entropy loss, and the second term is a regularization term for the contribution of the graph nodes. Here, W represents the personalized aggregation coefficients between different clients. The cosine similarity function is used to measure the similarity between theta I and theta j. And the final category about the global aggregation is composite aggregation. We found that existing aggregation functions used in federated recommendation tasks are primarily inspired by those in the federated vision community. However, they encounter challenges due to the disparate model structures between traditional federated learning and federated recommendation. Like in traditional federated learning, um, the models is often the convolutional neural networks, short for CNN models. And in federated recommendation tasks, the mainstream model structure is about embedding table. So this raises the question, can we design an aggregation method specifically tailored for embedding tables in FR tasks? We then analyze the issues with mainstream similarity-based aggregation methods, namely when relying solely on similarity aggregation, It leads to the unique embedding scale issue in FRS, where trained embeddings denoted in blue continue to improve, while non-trained embeddings noted in gray either remain unchanged or even bad during aggregation. We then analyzed the issue of embedding scale from an experimental perspective. We conducted experiments using an improved federated average model, where we aggregated parameters with the most similar clients, and the number of clients is increased by 10, from 10 to 100. As the number of aggregated similar clients increase, the accuracy of the training set continues to rise, while the accuracy on the test set generally declines across both datasets. From this, we can conclude that trained embeddings of interactive items are significantly enhanced, while untrained embeddings of non-interactive items gets bad during aggregation. We then analyze the embedding scale issue from a theoretical perspective. Formally, we denote Pxy as a joint distribution of features X and labels Y. So for two heterogeneous clients U and Y, it's evident that Pxu Yu is not equal to Pxv Yv. And the traditional thematic aggregation used in computer vision and traditional federated learning roughly models the data distribution as Pxy equals Py conditional on X, and only use model similarity to address heterogeneity, such as Pyu conditional on Xu is equal to Pyv equals on Xv. So by decoupling the joint distribution Pxy equals Px times Py conditional on X, heterogeneity can be represented as Pxu times Pyu conditional on Xu equals to Pyv conditional on Xv times Pxv. So the middle term is the model similarity used in traditional federated learning, and the Pxy denotes the data complexity used in our work, which is the contribution of data complexity. So by introducing the joint distribution Pxy equals Px times Py conditional on X, it's a fine-grained modeling of heterogeneity. So based on this, so this explains why introducing data complexity based on model similarity can help mitigate the embedding scale issue. So based on this theory, we propose a personalized FR model with composite aggregation, which not only aggregates similar clients to enhance trained embeddings, but also aggregates complementary clients to update non-trained embeddings. And from a global perspective, we integrate server aggregation and local training into a unified optimization framework, specifically tailored for federated recommendation tasks. The first term represents the task-specific loss, which is usually the cross-entropy loss function used in remounder systems. And the second term is about uh, the model similarity. And the third term captures the data complexity. So by flexibly adjusting the hyperparameters alpha, beta, and PV, this unified optimization framework can be adapted to recover several classic aggregation methods. For example, when alpha equals 0 and beta equals 0, and PV is set to average value, it corresponds to average aggregation in FCF. And when alpha equals 0 and beta equals 0, and PV is set to the relevant mm, data size, it can be weighted aggregation in federated average. So similarly, this setup can also degrade to other mainstream methods, including feed ATT, p-feed graph, per feed right, and feed fast. So these are the mainstream aggregation methods in p-feed reg. As we can see, they have gradually evolved from using uniformity parameters to personalized aggregation parameters. Additionally, earlier methods were primarily designed for general federated learning and didn't consider the specificity of the federated scenario. So a potential research direction for the future lies in designing aggregation methods that are more suited to the unique characters of the FR scenarios. So, okay, that's all the content about the global aggregation section. Hello, everyone. I will now introduce the server-side aggregation part. My name is Honglei Zhang, and I'm from Beijing Jiangdong University. First, I would like to express my sincere regret for not being able to attend the conference in person. This section, we will introduce the representative measures used in PFID to address the well-known communication efficiency issue. And we categorize these measures based on the different technical approaches they use, including reinforcement learning based methods, knowledge distillation methods, hashing based methods, row rank factorization methods, and neural architecture search methods. All these methods is used for centralized machine learning techniques, and they can be straightforward, be applied to uh, the recommendation scenarios in federated settings. And mm, it is not simply to apply the techniques into federated learning settings, and it should be adapted to federated recommendations for some tricks or for some federated variants. So the first category is reinforcement learning based methods. And as we all know, federated reinforcement learning is a type of machine learning where agent uh, learns to make decisions by interacting with created environments in order to maximize cumulative rewards. The agent takes actions, receives feedbacks, also known rewards or penalties, and learns which actions lead to better outcomes over time. And the advantage of reinforcement learning is about dynamic environment adaptation, sparse communication triggering, robustness to no ID data, and end-to-end communication optimization. So, an earlier work applying reinforcement learning techniques to federated recommendation tasks is FCF-BTS, which is published at the XM conference on recommender systems. And the core idea of FCF-BTS is to use Bayesian-Thompson sampling to optimize the upload and download of embedding parameters, and by defining a reasonable reward function, the method optimizes parameters between each communication round and selects the optimal subset of parameters, thereby improving communication efficiency. And from the experimental results, we can see the comparable performance under the significant payload reduction. So the reinforcement learning technique is useful for optimize the communication issues in federated settings. And this work is focused on the the item embeddings. And another work applies the multi-arm bandit framework on a neural collaborative built-in backbone to selectively transmit a smaller set of gradients. And the goal is to minimize the amount of transmitted gradient calculations while maintaining comparable performance. And from the results, we can also see the comparable performance under the baseline methods like NCF and the FNCF. The other recent work is FeedRL, which, unlike the aforementioned parameter transmission optimization, they primarily use a reinforcement learning selector to choose the eligible clients to participate in the aggregation. And so by defining a reasonable reward function for the multi-agent system, it selects an effective subset of participating clients to optimize efficiency. And from the right experimental results, we can also see the effectiveness of the proposed reinforcement learning method. And the second category to improve communication efficiency is knowledge distillation-based methods. And the core idea is to distill and transfer the knowledge from a large teacher model to a smaller student model, making its parameter smaller while ensuring the model's performance is preserved. So when we get the small but performance reached student model, we can achieve the comparable performance or even better performance and achieve the communication efficiency and memory efficiency, etc. Here, LLREG and ODREG apply the famous knowledge distillation in on-device recommendation task So to perform recommendation tasks on resource-constrained clients, a feature-based knowledge distillation method is used to distill a smaller student model from the pre-trained teacher model for next item prediction tasks. Additionally, TrustFR applies hierarchical knowledge distillation to transfer the knowledge from a large bird model to a smaller student model in a transfer learning scenario. And the distilled student model is then used in the item encoder to perform the next recommendation tasks and enabling efficient inference on resource-constrained clients. The third category, mainstream method, is a hashing-based methods, and the main idea is to encode high-dimensional data into compact binary codes, which helps to accelerate retrieval efficiency and reduce communication overhead. And the light FR is the first work to apply learning to hash techniques to the federated recommendation tasks. It proposed a federated discrete optimization method to optimize the binary feature matrix of users and items, thereby achieving fast online inference and economic memory consumption. And from the right experimental results, we can see the binary codes is very efficient in storage and communication cost compared to the dense codes. And another work, DFMR, building on the foundation of light FR, considers multiple behavior patterns in the context of heterogeneous single-class collaborative filtering. It introduced multiple behaviors to achieve a balance between efficiency and effectiveness. And on the right is the mean loss function used in this work, where the first term represents the discrete collaborative filtering loss used in light FR, and the second term most preference for the purchase behavior, and the second and the third term most preference for examination behavior. And the fourth category is low-rank factorization-based methods, such as the earlier matrix factorization and the more recent low-rank adaptation mechanism proposed for efficient training of large language models. And the core idea of matrix factorization is to most use item interactions as a product of low-dimensional latent factors. It approximates the original user item rating matrix by decoupling it into two smaller matrices representing user preference and item characters. Similarly, the low-rank adaptation, also known as LoRa, is a parameter-efficient fine-tuning method that injects trainable low-rank matrices into pre-trained models instead of updating all model weights. It learns low-rank updates, significantly reducing memory and computational costs while preserving preference. So the core idea of the low-rank factorization is to approximate the original large matrix using two small low-rank matrices, thereby achieving efficiency. The recent work named FeedLOCA decomposes global and client-specific knowledge from heterogeneous and sparse data into low-rank matrices, which are then aggregated to enhance global knowledge extraction and communication efficiency. And they use the recommendation laws, which is the cross entropy laws, and uh, this method is included two stages, and the one stage is called the warm-up stage, and the second stage is called the low-rank coordinated adaptation with knowledge decoupling. So at the first stage, they should to constraint the integrated embedding is as same as possible to the item embedding. And the second stage, they should to give a sparse constraint so as to improve the communication efficiency. So the main innovation here lies in using low-rank embeddings to simulatively achieve knowledge decoupling and efficiency improvements. Similarly, CoLR decomposes the parameters to be updated into two low-rank matrix B and A, and the B is initialized with a Gaussian distribution or Laplace distribution, and the A matrix is initialized by 0. So by doing so, we can achieve the same performance, the same purpose with the traditional matrix factorization, and then it only requires transmitting the smaller low-rank matrix A on the server side, so as to improve communication efficiency. And on the right experimental results, we can see the comparable results under the significant payload reduction. And the final category for improving communication efficiency is neural architecture search method. And this method is an automatic machine learning paradigm that searches for optimal neural network architectures for a given task. It replaces manual architecture design with a data-driven algorithmic approach, enhancing both performance and efficiency. And it replaces manual architecture design with a data-driven algorithmic approach. And the famous and the important component in neural architecture search is to firstly define the search space and the search strategy and the performance estimation strategy, so we can exploiting the search strategy to find a good search space to improve the algorithm efficiency. In the federated recommendation scenario, the key to applying a neural architecture search lies in defining the search space in a distributed setting. Therefore, this work distinguishes between federated architecture search and federated parameter search, and defines the search spaces at both the micro level and the macro level, aiming to reduce parameter transmission. So the optimal neural network architecture search includes the macro level and macro level. So the macro level search focuses on connecting neural operators within cells, while the macro level search determines the number and connections of cells to form the global model. Okay, this concludes the introduction to methods related to communication efficiency. It can be observed that these methods have gradually evolved from being designed solely for traditional federated learning and computer vision tasks to be adapted the special characters for recommendation tasks. And moreover, earlier, earlier methods primarily focus on improving efficiency. So a future research hotspot will be how to balance efficiency with with model performance. Okay, this is the section about the techniques introduced to improve the communication efficiency. Okay, that's all. Thank you. This section, we will introduce the representative measures used in
Okay. That's all for today's tutorial. Here is references that you may check for. There are our tutorial on personalized federated recommenders. Recent advances and future directions is over. Thank you for your participation and attention. Now it's Q&A time. Please feel free to ask questions and share ideas with us.